Let's consider another definition for function d. We have to show that d of x and y is equal to the square root of the absolute value of their difference. And we're going to show that it's a metric on our set of real numbers. When I talk about metric, there are 4 conditions that should be met before we can say that a certain function d is a metric on the given set. So we're going to show it here for this video. The first condition, we coined it M1. For the first condition for a metric, we need to show that the function d of x and y, or distance of x and y, as given by the definition here, should be greater than or equal to 0 for all x and y element of our set x, in this case, set of real numbers. So we just need to show that it's positive, or 0, or 0 is the smallest possible value in all positive numbers of real numbers. So we know that the definition given here is that for this function to be given as, you have here, distance of x and y is equal to the square root of the absolute value of x and y. Now, take note that our x and y values are element of our set x, in this case defined here as a set of real numbers. And whatever we apply here, this will always be greater than or equal to 0 because of the absolute value notation. Okay? And even if we have the square root or radical expression here, given that this value is greater than or equal to 0 because of the absolute value notation, this will always be equal to or greater than or equal to 0 no matter what the value of the absolute value is. So we have established here that M1 is already satisfied. No matter what the values of x and y are, under absolute value notation, it will always be positive or even 0 if they are equal, and the square root of that will always be greater than or equal to 0. Now let's proceed to M2. M2 states that if the distance of x and y is equal to 0, we can say that this is only possible if and only if x is equal to y for all x and y element of our set x, or in this case, the set of real numbers. So since this is a bijection, we need to show both ways. Let's start with the if statement. So we are going to assume that the distance of x and y is equal to 0. If that would be the case, per definition, this is square root of the absolute value of a difference of x and y equal to 0. So our goal is to show that x is just equal to y or vice versa. Take note that this entire expression will only be equal to 0 if the radicand of this radical expression is also equal to 0. So that would mean the radicand, being the absolute value notation, is equal to 0. Because if it is, the square root of that will always be equal to 0, right? Then with this in mind, if the absolute value of the difference is equal to 0, this is only possible if the expression inside here is also equal to 0. Okay? And with that, by moving y on the right hand side, we have shown that x is equal to y for the first condition. Now, for the other movement, the backward movement, we're going to assume that x is equal to y, and we need to show that the distance using the given definition is equal to 0. So if they are equal, our distance of x and y, which is defined as the absolute value, the square root of the absolute value of their difference. And since x is equal to y, we can substitute x to y or y to x depending on your decision. Let me choose here x and x because x is equal to y. This would mean that its absolute value, the square root of the absolute value of a difference of x and x. With this is actually the square root of the absolute value of 0, square root of 0, this is equal to 0. So cutting all of this, we have shown that if x is equal to y, we have shown that the distance of x and y is equal to 0. With those two conditions for M2 has been met, we can now say that M2 is already satisfied. Okay, now let's proceed to our M3. This is for symmetry. M3 symmetry tells us that the distance of x and y is just equal to the distance of y and x. So no matter which value is written first in our function later on, so they are just the same for all x and y element of x, or the set of real numbers for this case. So we need to assume this and show that it will reach here. Take note that if we have this definition given here, this is our definition. This is just equal to the square root of the absolute value of x and y. Okay? Now, looking into the radicand itself, we can always rearrange the radicand, the entries of the absolute value notation just like this. It's minus y and plus x. We did not change the value, we simply rearranged them. Now, what if we factor -1 for this expression? So you will have positive y, and your plus x becomes minus x because you factored -1. Now with this at the bottom, we can see that there is a constant here in an expression, and they are under absolute value notation. There is a property for absolute value that we can separate the scalar constant and the expression. In short, the product of a scalar, or the absolute value of the product of the scalar and any expression is equal to the product of the absolute value of that said scalar and the expression itself. Of course, the absolute value of -1 is 1, so you will have an expression like this here. And what does this stand for? This is actually equal to the distance of y and x. Following that, we have here x first earlier and then y now, and y here and x. So we have shown that the distance of x and y is equal to the distance of y and x. Hence, M3 is now satisfied. Okay? So let's proceed to our last one, and hopefully my spaces here is enough because it will take a longer process here as we deal with M4, which is on triangle inequality. Let's assume that there is a distance of x and z. Triangle inequality tells us that if there exists a certain y between x and z, this is always less than or equal to the sum of the distances of x to y and y to z for all x, y, and z element of our set x, or the set of real numbers. One proof that I could show you here is the idea that we have here this expression per definition is equal to the square root of the absolute value of the distance, the difference between x and z. Now, since we have a radical expression here, some proofs allows us to square both sides of the equation so that our radical expression will be removed, and such that, this is z by the way, such that we could actually work on absolute value instead of the radical expression. So we have here, take note, this is still, since we are squaring both sides, we're going to return to that later. Hopefully I have some spaces here, but if I don't have much space, I'll be using some spaces at the top. Okay, so with this now, this becomes the absolute value of x and the absolute value of a difference of x and z. Now, in the previous example or video, we have also shown that this is less than or equal to x minus y, the sum of the independent absolute value notations x minus y and y minus z. Please try to review the previous video for this. Okay, so with this already established, we can also add a certain something here that will still be greater than or equal to that, because once you add something to already a larger value to the other, it will also still stay as a larger value. What I would like to add here is this. So of course you have something like that, something like this here. I would like to add here this certain expression plus twice the square root of the product of the two. Okay, so we have here the square root of this, okay, and you have here yes, the product, so square root times square root. Don't worry about that one. Okay, or you can separate them as product, right? Okay, now with this in mind, don't worry about not adding the same on the other side, because we are not retaining the equality, what we would like to do so is to show that if this is less than this expression, and if we are to add another, this is still less than to that. The reason for that is this entire expression now can be expressed as a perfect square trinomial. Okay? So this is now, when rearranging this, you can have the absolute value of x minus y plus twice the square root of the product of the independent absolute value notations, that's z, plus you have your absolute value of y minus z. And when you have to apply here this is a perfect square trinomial, you're going to apply it. This will become the square of a binomial, and that binomial will entail to this. So this is equal to, I'm using equal to this expression here. Okay, so equal to the square of the binomial x absolute value. Sorry, I forgot to write absolute value because I'm just using this inside here. X minus y plus the square root of the absolute value of y minus z. Okay, that's absolute value, so that's square, which is just equal to this and equal to that, which is still greater than this here. Okay, so bear with me once you look at this one. This is just equal to that. Okay, equal to this one here. So this is again the square of the distance of x and z, and this is entirely less than or equal to this form here. Okay, this form here at the last. So you have here the square of the expressions. Let me have, again, I don't have much space here, sorry for that. I might be using some spaces here later, or I'm going to use it now, okay, for your benefit. This here, let me use some spaces somewhere here. Okay, I'm going to add to that. So the distance, the square, sorry for that, the square of the distance at x to z, this one here, sorry, this, which is equal to the absolute value of x minus z, which is less than to this, to that, to that, to that. So we can say here that this is less than or equal to the last form, the square of the binomial expression, okay, plus square of y minus z. Okay, then let's try to take the square root of both sides, removing the exponentiation. You have here distance of x to z is doesn't equal to, you have this expression here, x minus y plus y minus z. And what are these two? These are actually distance using the definition here. So bottom line, we can say now that the distance of x and z is less than or equal to the distance of x and y, which is this, plus the distance of y and z, which is this. So this is M4. So we have satisfied M4. Then to this one here, we used the idea of exponentiation before we started earlier for M4 so that we could remove the square root signs, and we have something like this here. So now, since M4 is satisfied, M3 is satisfied, M2 and M1, now finally we can say here that D, therefore D is a metric on our x, which is a set of real numbers. And further, you can say that this expression is a metric space because we have already shown that function D is a metric on the set R. That's it for this video. Thank you very much for watching.